Welcome guys. So this video is the quick proof of the Fermat 4n+1 theorem. So basically the statement is that the theorem is that if p is prime number and p is 4n+1 type, so which n is integer. So basically, or this is equivalent to see that p is the 1 mod 4. Sorry, let me clean the p. So p is 1 mod 4, and the p is prime. Then p is p can be written as x squared plus y squared, where x, y are integer. Okay, so this is the Fermat 4n+1 theorem. So for example, before diving the proof, because what we need to use the algebraic proof. So the proof is really easy. So what we first show some example. So 5 is 4n+1. 4 times 1+1, so it's 1 squared plus 2 squared. And the second, I think, is 7. So 7 is not 4n+1, and 11 is not 4n+1, but 13 is 4n+1. So 13 is 4 plus 9, and then we can keep doing. Okay, so the proof in this video, what we use is the algebraic proof. Okay, so the technical is that technically what we need to use the zi. Basically, is the a plus bi, which a b are integer. So this is called Gaussian integer. Okay, so basically and the usual addition and multiplication. So what we know is that at least the zi is a commutative ring with identity. Okay, so this is the fact, which is trivial. But the non-trivial is that the z of I x is Euclidean domain. Okay. So let me remind you that what is Euclidean domain. So basically, zi basically the subset of R, right? So zi is also integral domain. Okay, so zi is already a domain. Difference zi is an integral domain. So that means there exists a form, norm. I should say norm. Okay, I write n R. So let me definition is that there is a norm from the Gaussian integer to integer natural number union 0, such that for every x, y belongs to z of I, and the y is non-zero. What we have is first one is that the x can be written as y times b times r. So this is like a division, such that by the way, these br are in the zi, which n of r is less than n of y, or n of r, or r is 0. So we have two cases. Given any x and y, we can directly do the division. Okay, this is the first one, and the second one is that I need to satisfy this. So if b is non-zero, then a, if take any a times b, then it must larger than so it must increase. Okay, so the key point is that I can define n of a plus bi to be this is not norm. So I can define to be square root of a plus b, a square plus b square, a square plus b square. Okay, so what we need to show is that so basically you can check this NAB, because NAB is just NA times NB, and if b is non-zero, that means n of b must larger than 1, because this b is just real b square plus image b square, and the b are just integer. So this is common sense. Okay, so the difficult point is the first one. Okay, so the first one is that given x and y, so you can write down this. Okay, but this can be proved by the geometrical picture, which you draw a line from x and y, and these are 0, these are 0. So this is a Gaussian integer, right? And then you can draw any circle, a radius 1 circle along this Gaussian integer. Okay, and you will find that given any points in the plane, then you can always find a Gaussian integer, which the distance. Suppose you choose this point, call it x, and so for any x in the complex plane, and you always find x bar, which is a Gaussian integer, such that x minus x bar, the distance is less than square root divided by 2. Okay, so this is a geometrical picture tell you. Okay, so from this point of view, that we can prove this fact. Okay, the proof is that suppose somebody give you x, so now you have x and y, and the rest is just try to find b, right? Okay, so what I can do is I can try to write x equals to let me see. Okay, so because by plus r, right? So I can try to write x minus by just r, and I divide by y, so I have this. Okay, and if I take the norm, I have this, and I can take y. So if I take, so this is n of r, and from this I can choose b. So b is a Gaussian integer such that x minus y is so I can choose a b which their distance is less or equal to this, right? So this is the geometrical meaning. So we tell you that n of r can be less than n of y times this one, definitely less than n of y. So which tell you that zi is an integer, is the Euclidean domain. Okay, so the theorem is that z of I is Euclidean domain, and from the abstract algebra we know that z of I is a unique factorization domain. It's a unique factorization domain. Okay, so up to now we are good, because by the way, we need to use another theorem. So another theorem is that so if p is 4n+1, then there exists a number called m in the integer, such that m squared is minus 1 mod p. So I will not tell you how to prove this, but I guess it's very easy in the number theory. So I just mentioned the fact that m squared is just minus 1 mod p. Okay, so from here, what we are ready to prove. Okay, so the key is that so now we know that m squared plus 1 just p is just divisible. p divides m squared plus 1. By the way, and m squared plus 1 is m plus I and minus I. So this is the factorization in Zi. Okay. However, p does not divide m minus plus I. P also not divides m minus I. And the reason is that if you take the absolute value of p, then you got p. But you take absolute m plus I, you get square root of m squared minus I plus 1. And you know that there's m squared plus p divided by p is not form of a squared plus b squared. This can easily be seen because m is not, because if you can move the p into the square root, then you see which is not a 2 square sum. Okay, so m does not divide m plus I, m does not divide m minus I. So which tell you that p is not prime. P is not prime in Zi. So this is important that p is prime in the Z, but p is not prime in the Zi. P is not prime in the Gaussian integer. Okay, then what we have is p is just what? P is just can be written as sum of 2 alpha beta in the Z of I, right? However, since p is a real number, so if you can write down 2 real numbers in and also n of p is just p, n of alpha, n of beta. Okay, so it depends on you. I mean, I can say that. So if I square it, I will have p squared equals to n of alpha squared, n of beta squared. However, so n of alpha is square is the square of real alpha squared plus image alpha squared. So which is also integer. So this is also integer. So the only remaining case is n of alpha be p, or n of beta be p. This is one way, and the other way is n of alpha be p squared. No, n of beta to be 1, or vice versa. However, this is impossible, right? If n of beta is 1, then then beta is only plus 1, plus or minus 1, or plus I or minus I. So this is not a factorization. Okay. So since we know that p must have some non-trivial factorization, so the only factorization is n of alpha equals to p. So which tell you that there exists alpha 1, alpha 2, such that alpha just equals alpha 1 plus I alpha 2, and n of alpha equals to p, which tell you that the square root of alpha 1 plus alpha 2, which is p. So which is alpha 1 plus alpha 2 equals to p squared. Equals to p. Okay, so this is the whole proof of the Fermat 4n+1 theorem by using the Gaussian integer. Okay, so the key fact is that Z of I is a Euclidean domain, implies Fermat 4n+1 theorem. I think next time we will use the Minkowski theorem to prove this result and a more difficult result called the Lagrangian 4-square problems. Okay, so this is my video, and I think which is interesting and amusing. I will see you guys in the next video.